Hello, everyone, and welcome to the last Quantum Mike Classic episode. As you might know at this point, the Quantum Mike was originally a podcast that I did during my undergrad, during the COVID period, where I interviewed people who are involved in physics. This is a very special episode, as it was the last interview I ever did for the podcast version of the Quantum Mike back in 2023, and it is extra special because I got the privilege to talk to Nobel Prize winner Dr. Arthur McDonald and talk to him about the SNO experiment. So if you're excited to listen to that, please plug in your earbuds and you'll very much enjoy it. It's a very good episode. Okay, have a good one. Hello everybody, welcome back to the Quantum Mike. Today I'm honored to be joined by a very special guest, the 2015 Nobel Prize Laureate Dr. Arthur B. McDonald. Thank you for joining me today, Dr. McDonald.
Oh, it's a real pleasure. I applaud you for doing this sort of podcast to try to put information out to people.
Oh, I think it's very important for people to be informed about what's kind of going on in science or what has gone on. So before we get into it, I think some of the listeners may know who you are, some of them may not. So would you mind sort of introducing yourself, talking about who you are, your sort of experiences?
So I'm originally from Sydney, Nova Scotia. I went to my undergraduate work at Dalhousie, took a one-year master's and then went to Caltech where I got a PhD in nuclear physics in 1969, worked at Chalk River Nuclear Labs from 1969 to 1982, was a tenured professor at Princeton from then until 1989 when I moved back to Queen's University, and I've been there since then. I retired in 2013, although I'm still active in research here. And I started working on the SNO project in 1984 as a part of the 16-member group that was the initial stage of the collaboration.
Okay. Some of our listeners may not know about SNO. We've kind of had a few interviews where I've brought it up, especially we had talked to someone who was working on NEXO, where they were considering proposing to have it put in SNOLabs, but we haven't talked about SNO itself. So would you mind describing what the SNO experiment is? What was it looking for when it was originally started?
Yeah, so the SNO stands for Sudbury Neutrino Observatory. And what we were looking for was neutrinos from the sun, neutrinos from the nuclear reactions that power the sun. People may not even be very familiar with neutrinos. They are, along with electrons and quarks, they are the basic building blocks or fundamental particles that we don't know how to subdivide at this point. And they are basically the essence of the standard model of particle physics, along with the forces that interact between the various particles. Neutrinos only feel the weakest of the forces, which is called the weak force. And so they are very unlikely to be affected by even passing through large amounts of matter. They can pass through the amount of lead corresponding to the distance that light travels in a year, about 1 billion kilometers, with only about a 50% chance of interacting, because only if they hit the nucleus of an atom or the electrons going around it head on do they stop. And so neutrinos are excellent for attempting to study the nuclear reactions powering the sun, because there are billions and more of neutrinos being produced every second from the sun. In fact, there are billions of neutrinos per second going through all of us. On the other hand, they are, and that makes them very nice when it comes to trying to understand these nuclear reactions. On the other hand, they're very difficult to detect. And so the Sudbury Neutrino Observatory was a detector the size of a 10-story building. It had 1,000 tons of very valuable heavy water that normally is used as a moderator in Canadian-style nuclear reactors, which gave it a significant scientific advantage in studying these neutrinos. In 1984, when we started the project, in response to a suggestion from Professor Herb Chen from the University of California at Irvine, scientists here in Canada investigated whether it might be possible to borrow enough heavy water to make a measurement of neutrinos from the sun interacting with it. And the answer was yes, at a level of about $300 million worth, which is what we eventually obtained. Others were very actively involved. Professor George Ewan from Queen's University, along with Professor Chen, were the two original spokespersons for the project. And it was a Canada-US project to begin with. David Sinclair from Carleton in 1985 brought the Oxford group into the project and later served as the deputy director throughout the project. Professor Chen passed away in 1987, and I became the US spokesman and then took over as director of the project when I moved back to Queens in 1989. But the idea was to solve what had come to be known as the solar neutrino problem. Neutrinos had been detected from the sun by an experiment run by Professor Ray Davis, for which he received a Nobel Prize in 2002, actually after our first results came in, confirming that his measurements were correct. But he observed only 1/3 of the number of neutrinos that were expected to be produced by the available reactions or measurable reactions from the nuclear reactions in the sun in comparison to calculations done, which were very sophisticated and done predominantly by Professor John Bacall. The question was, is the experiment or the calculations, are they either one of them incorrect, or is there another process taking place which would be beyond what was currently being predicted by the elementary particle standard model, the process being that neutrinos of the type produced in the sun, electron neutrinos, were changing into other types, muon or tau neutrinos, before they reach his detector. With heavy water, we could measure one reaction that was specific to the type of neutrinos produced in the sun, as was Ray Davis's measurement. And so we could measure that number very accurately, but we also could measure the total flux of all neutrino types, even if there had been this change of neutrino type taking place. By having any neutrino coming in and basically breaking apart the deuterium, which is the heart of the heavy water, D2O, that extra neutron added to the hydrogen nucleus makes it heavier without changing its chemical properties. If that neutron is knocked out by an incoming neutrino, then you have a measure of the total flux, even if there has been a change. And if you compare the number of electron neutrinos with the total, you can tell whether or not there has been this change into other neutrino types. That's exactly what we observed. We observed it with high accuracy. Eventually, the accuracy that was required by particle physics for an acceptable discovery, that is a chance of less than 1 part in 10 million, or 5 standard deviations, as it's called in the analysis process. And so that is what the Nobel Prize was awarded for. So from that perspective, it was a major effort. It took from 1984 until basically 2002, when we had those confirming measurements. Over 200 authors on our papers, over 700 people actively working on the project, and a total of about $100 million expended in order to make those measurements. But it was very significant because it's the first piece of physics beyond the standard model, and it shows at least part of the way for trying to expand beyond the standard model and understanding our universe more completely. So it's a very long answer to your question about how SNO started, but at least it gives you a feel for how this developed and what the final results were.
It gives a very good feeling of what the experiment was and the results. That's a really impressive experiment just in general, the amount of people involved in it. And actually, since you were director of SNO, what was kind of different from being someone who did experimental physics and was probably been part of worked on experiments, worked on projects, to moving to being the director, the person kind of in charge? What was the sort of difference between those two sort of environments, especially with such a large project as SNO ended up being?
Well, it's very important, whether you're working in a small group or a large group, to be intellectually involved in all aspects of the project. Particularly as the director, you have to understand the scientific motivation. You have to understand the technical details in order to make sure that the measurements you're going to make are going to accomplish what you are going to set out to do. And of course, you also have to have solid arguments to convince funding agencies to provide you with the money to do this, especially when you're proposing to do something that is above the scale of what Canadian funding agencies are at that time were typically prepared to fund. However, you have a tremendous advantage in a major experiment in that you have all of those extremely competent collaborators that I mentioned a moment or two ago. And that really was a large part of my job, was listening, discussing, attempting to make sure that the way in which everyone interacted was very positive and focused on the scientific goals. You often had differences of opinion. Really, they were usually several good ideas being put forward. And the approach that we took to it was to try to discuss them as completely as possible and ultimately come up with a consensus as to which was the better of the two ways that were being put forward for a specific thing. In some cases, we had to, the collaboration had to develop new technologies in order to accomplish what we wanted to do. And that was a significant advantage as well. We worked with commercial companies to improve their products in some cases, and in some cases, develop things ourselves. And so overall, it was a complex process. For me, it was taking place in Sudbury, which is some distance from Queen's University, where I was a professor and still had certain teaching responsibilities. That's not different for the remainder of at least the faculty members in the project, but also for a number of our students and postdocs who did always spend a certain fraction of their graduate time on site working on construction or operation of the detector. So they got that hands-on experience as well as significant data analysis. But I spent a lot of time in Sudbury, just trying to make sure that I was there and therefore knowledgeable about the way in which the project was proceeding. We were able to hire an experienced project management and engineering company because this was an enormous task. And I had to work very carefully with them in order to make sure that we accomplished the engineering of it, and also to try to coordinate although I had a lot of help with that from my fellow scientists, coordinate between the engineers and the scientists in order to get what was engineered to be something that met the specifications of the science. A very, very interesting experience. And of course, we had times when we had to work hard to solve problems that came up. And that's where having a broadly experienced and talented group of collaborators is what made it possible for us to go forward.
Oh, that's really kind of inspiring to hear about, honestly, especially since I've so far mainly talked to individuals who have been sort of at the lower-ish levels of working on a project, such as the SNO experiment. To hear about how it works from the upper level, especially one that's, I want to say it's so old, but it's been around for a while now. It's kind of inspiring just to sort of hear about the amount of effort that needed to go into it and the complexity of it.
Well, actually, you mentioned people working at, quotes, the lower levels. It turns out that, I used to say, and it was true, that even the people that swept the floors were as important as everyone else in this project, because we were trying to maintain extremely clean conditions and avoid having any significant radioactivity that might interfere with our signals. But in fact, the way these large projects are organized on the scientific and technical side, they're broken down into a number of sub-projects where a particular object is being engineered or scientifically developed, or where an idea is being tested, and so on. And so organizing, even at what you referred to as the lower level, I would simply call it the more detailed level of the project, is somewhat similar to the organization that you have at the overall level, in the sense that you have to have a well-defined task. You have to have members of the small group that's working on it know what their tasks are. You have to have adherence to a schedule and a budget associated with it in order to contribute. And then all those detailed parts get put together. And so even if you're working at, let's call it the more detailed level,
Mm-hmm.
just as important as the overview in terms of the project being successful.
Yeah, of course.
And it's also good experience for moving.
Oh, yes, definitely.
broader aspects of managing a big project.
Yeah, definitely. It's just really fascinating, especially since it's something that I haven't learned a lot about or heard a lot about the different the experiences of managing these scientific experiments. We don't usually talk about that. We usually talk about the results. I think it's kind of neat, something that people don't usually hear about. So talking again about SNO, SNO is being upgraded or has been upgraded to SNO Plus. I don't think I could remember if it has been upgraded or not, but is that correct?
Yes, in part is what I'll say at this point. SNO Plus is directed by my colleague Mark Chen, who's a professor here at Queen's, and it again is a large collaboration that has the ultimate objective a search for a very rare radioactivity referred to as neutrinoless double beta decay, for which the half-life is on the order of or greater than 10 to the 26th years, which is an awful long time to wait to see something decay, but it's not so daunting if you realize that, Avogadro's number, 6 times 10 to the 23rd, is the number of atoms in a mole of material. And so you can start with a fair number of atoms, especially if, as in this case, you can put 4 tons of the material that you are wanting to study and look for this rare decay, which in our case is tellurium. I'm still involved in the project, but in a much more minor way, and Professor Chen is directing it. So the idea is to take the SNO experiment that used to have a central volume in an acrylic sphere looked at by 10,000 light sensors in a cavity the size of a 10-story building, 2 kilometers underground, with strong cleanliness maintained everywhere in the whole laboratory, but also within the detector itself, and to avoid having mine dust that creates bits of radioactivity from uranium and thorium in it. So ultra clean conditions. The heavy water has been removed and replaced first with ordinary water, but highly purified, and now with highly purified liquid scintillator, as it's called, material called linear alkyl benzene, which with a wavelength shifter or converter called PPO can give you up to 50 to 100 times the amount of light that you would get out for an interacting fundamental particle compared to what we were obtaining from the processes we were using in the heavy water. So the idea is to look for a decay of this particular nucleus, tellurium-130, which is 36% of natural tellurium, in a way that 2 neutrinos are emitted and two electrons are emitted and no neutrinos are emitted. The normal process would be simply 2 ordinary beta decays where a neutrino and an electron are emitted, and so you would have 2 neutrinos and 2 electrons emitted. In this case, if the neutrino is its own antiparticle, it can be there can be a situation where basically within the nucleus they annihilate each other, the 2 that might have been emitted, and none are emitted. In this case, gives you, for the sum of the electron energy, a monoenergetic peak, which is what is looked for. So the reason why this is of interest is to understand the properties of neutrinos. If you're trying to come up with that extension to the theory of the standard model in order to understand how neutrinos turn out to change their flavor and have a finite mass, but it's also of relevance because it's thought that those processes also contribute to the way in which antimatter has decayed away in the early universe. We think that in the Big Bang, energy is converted into equal amounts of matter and antimatter. But of course, we don't see antimatter in this universe. We see only matter. And understanding those properties of neutrinos, if we can observe this very rare process of neutrinoless double beta decay, can give us information about the theory of how that happens in the early universe. So it has a cosmological as well as a particle physics motivation to the experiment. Right now, the experiment is running with the liquid scintillator and PPO in place, and a lot of information is being obtained about the radioactive backgrounds, all of which appears very favorable to making a sensitive measurement when the tellurium itself is dissolved in a particular organic compound in the liquid scintillator starting in 2024. So it's very close to starting the actual measurements on neutrinoless double beta decay. But in the meantime, there are other measurements of neutrinos from the sun and neutrinos actually from the Earth that can tell us about uranium and thorium content down hundreds of kilometers. About 40% of the heat flow out of the Earth comes from such uranium and thorium content. So it's of interest geologically, but also we can detect neutrinos from Darlington and Bruce, for example, in terms of raw oscillations. So it already has a number of interesting physics things to be done, but the ultimate goal is neutrinoless double beta decay.
Fascinating. So it's good to know that SNO is still being used through all these years. And actually, talking about snow, I'm gonna move on to something else, if that's okay, which is SNOLab. Which, well, you know what SNOLab is, but for the people listening, SNOLab is an extension of around where the snow experiment is, as a laboratory location with a number of other experiments. How did the snow experiment turn into sort of the location that is now SNOLab? How did that change sort of occur?
So after the success of SNOW, which took place at the point where we published our 5 standard deviation result in 2002, there was another phase that took place in the following roughly 2 years. But around the same, and that second phase was a large part of the work of Professor David Sinclair there at Carleton. And it was very successful as well. It gave us enhanced sensitivity. But around the same time, the Canada Foundation for Innovation put forward an opportunity to apply for the creation of laboratories in Canada of a substantial nature that would attract international scientists to come to Canada and work with Canadians on major projects. And again, David Sinclair was the leader of an application for SNOLab. As I said, he was a deputy director at that point, and there was a further phase of SNOW that was to take place. But basically, he was a logical leader for this, particularly since Carleton University was also prepared to step forward and lead the construction of the laboratory, working again with a major engineering firm. And so he basically applied for, obtained the funding, and the expansion took place over the next few years, giving a total excavated volume that was expanded by about a factor of 3, and now hosting about 6 other major experiments, many of which are looking for dark matter particles, which we now know that are not neutrinos. When we first started SNOW, we thought maybe neutrinos that to some degree meet the characteristics for the particles that constitute dark matter, and that they are weakly interacting and very prolific following the Big Bang, but they're not massive enough. And so these new experiments look for weakly interacting massive particles in experiments in the new SNOLab. So SNOLab has really become a major international facility. It is the lowest radioactivity location in the world, quite comparable to a new laboratory that's been developed in China in terms of the numbers of muons produced in the atmosphere that penetrate through and cause problems in the experiments. These are the deepest laboratories in terms of getting rid of the muons by the rock above. But SNOLab is the only lab where the entire laboratory is a class 2000 clean room, giving tremendous advantage when you're trying to build these hermetically sealed and extremely radioactively clean, dust-free experiments. And so it has a legitimate claim as the lowest radioactivity laboratory in the world. And it's turning out that major experiments, in some cases in excess of several $100 million, you mentioned you've already had a podcast relating to NXO, which is one of the ones that has stated that SNOLab is definitely where it wants to be located. It's a neutrinoless double beta decay experiment, but also potentially in the longer term, the Argo experiment using liquid argon, a major expansion by a factor of 100 in size over the deep experiment led by Professor Boulay from Carleton, and perhaps taking place 10 years from now. So, and in that case, the major international collaboration has also targeted SNOLab as a location of interest, the central location of interest. So SNOLab is very successful, and it is, in fact, putting Canada on the map as a substantial contributor at the frontiers of particle physics.
That's really cool to learn about. I've been to SNOLabs once back in during my first year. We had the opportunity to go with the Physics Society. And it's quite an impressive facility. It's so far below the ground. The clean room is very impressive. It was amazing to go visit.
Yeah, it's pretty unusual. You go down along with the miners in a elevator. It's called the cage. It looks like a cage.
Yeah.
About 40 kilometers an hour, I think, straight down. If you get a trip all the way to the bottom at 2 kilometers down. And it is then, as you walk through the mine, quite amazing to walk into this ultra clean facility where you actually are required to change into lint-free clothes, take a shower and change into lint-free clothing in order to keep the dust out. And that works very well. And the experiments that are being housed there are extremely sophisticated, having various ways of being sure that they do not register significant radioactive events, if you're looking for dark matter, but are very sensitive to dark matter particles, causing the nuclei in the experiments to recoil. And these various techniques involve a number of different target nuclei. The deep experiment and the Argo experiment use liquid argon. There are others that use helium, fluorine, germanium, silicon, and they all have their own little hook as to how you can get rid of the radioactivity and still maintain your sensitivity for dark matter. So technology is right at the frontier for all of these experiments, and there are spin-offs that happen as a result as well.
Yeah, I think that's really awesome. And there's this major international underground laboratory in Canada, in Ontario even. It's really neat.
Yeah,
and
I agree.
Sorry.
I agree with you. It's neat to have this major national and international laboratory in Ontario and here in Canada. But one of the big aspects of it is that we are able to educate continuing generations of students and postdocs who are working at the cutting edge of the field of particle physics. This is physics that has similar significance to what's happening at the major accelerator laboratories around the world that gets a fair amount of publicity. The Large Hadron Collider at CERN, for example, is attempting to produce dark matter particles for the first time since the Big Bang, with the idea that we haven't observed dark matter before because we simply haven't had the energy to produce them, whereas we did back in the Big Bang, and we know that dark matter particles are here because of the influence they have in holding our galaxy together. And so we can present targets for these dark matter particles and test their potential for interacting with ordinary matter with these measurements. At the same time, Fermilab is spending the majority of its experimental program on a long baseline neutrino oscillation experiment where they shoot a beam of muon neutrinos and muon antineutrinos to a detector in South Dakota, 1,300 kilometers away, I believe. And they look for another element in this question of how does the antimatter decay away in the early universe. Similar thing is happening at the J-Park, the major accelerator facility in Japan. So the topics that are being addressed at SNOLab are very, very much on the front line of what's of interest in particle physics today. And that's very valuable to have that facility here in Canada, and very good for students to be able to do this sort of thing here at home.
I definitely agree. Actually, as a student who got involved with the deep experiment during my second year, and now doing stuff with the Atlas group here at Carleton.
Great.
It was a great opportunity to just be able to do things that were semi-relevant to what was going on in Canada, like here locally. It feels weird doing something that's not quite as locally attached when working on things. I don't know. It's weird, but as a student, it felt more inspiring to go do physics when you could. I mean, Ottawa's still pretty far from Sudbury, but nonetheless, there's a place here that you could go to, and it is being done, quote unquote, locally within the country.
I agree with you. The Atlas experiment is one of the major experiments at the Large Hadron Collider that is looking for dark matter particles as well as a number of other things.
Mm-hmm. That's actually what I'm working on, a thing that one of the professors at Carleton helped with a paper on emerging jets. So that's what which is a potential phenomenon from a beyond the standard model dark matter model. That's not very well worded, but
well, that's great.
It's neat. Anyways, back to you. This is your interview. We're talking to you. So along with SNOLabs, I am also aware of, and it's probably partially due to being a Carleton student, and I've worked with Dr. Simone Veal, who's part of the Institute, but there is an Arthur B. McDonald Institute. There is an institute with your name. How did that come into being?
Well, it came into being mainly from a lot of hard work by Professor Tony Noble here at Queen's, in collaboration with scientists working in particle astrophysics across the country. And there was, again, a government competition called the Canada First Research Excellence Fund, which was intended to support emerging fields of research in Canada, innovative fields. And so Tony worked very hard and was able to get an amazing grant, $63 million over 7 years, which, according to what was applied for, was able to provide 15 new faculty members in this field across the country, supported for that 7-year period by the McDonald Institute. By the way, they ended up naming it after me because the Nobel Prize came along shortly after the Institute was approved. Somewhat unjust given the fact that it's Tony who has done all the work and continues to do all the work, including a submission for a new potential grant for the longer term. But nevertheless, the Institute has my name on it. I'm very grateful for that, but don't get the idea that it's me that created it. I would have if I I like it, and I would have if I could have, but Tony did work, put it that way. Simone Veal is one of the McDonald Institute faculty that was hired, and there are hundreds of students and postdocs that have been supported by that funding. There's a tremendous outreach effort that's being put out, and really it provides the next generation of faculty, students, postdocs to take advantage of this tremendous international facility we have in Canada. Not that that's the only thing they work on. There are people also working on experiments that are not situated there, including, for example, the ice cube experiment at the South Pole. but generally experiments that are in the field of astroparticle physics, which is another part of the name of the institute. And it's been very successful.
That's amazing. That's awesome that there's an institute designed to help with getting people who are coming into the field engaged and involved.
Yeah, we've been very fortunate in terms of the support from the universities for this activity and the hard work of the people who have continued to go beyond the SNO project and make sure that this field of astroparticle physics, which is becoming a very large part of particle physics compared to what it was 20 years ago, that this is successful and that Canada has a big role in it.
Yeah. So looking at the time, we're kind of getting close to the end. So I have two questions I really kind of want to ask you. So I'm going to ask those to you now.
Okay.
Question number one. So you're currently now retired, but you said you're still working on research. Is there any research that you're currently working on that you're really interested in or very passionate about right now?
Certainly. I mean, I have let's say an overview relationship to the SNO Plus project and to the projects that are using liquid argon for the detection of dark matter. Argon has a very interesting property that if you have a nuclear recoil, the light emitted comes out in less than 10 nanoseconds, whereas if you have gamma or beta radiation, it can take many microseconds for the light to come out. And so we can discriminate against those gamma and beta radioactivities by factors of greater than 10 to the 8th, which has been demonstrated in the DEEP experiment with 3 tons of liquid argon. The collaboration in Canada, as I mentioned, led by Professor Boulay and Professor Axel Hallin at Alberta, is also now working on the dark side experiment, which is effectively about 7 or 8 times more volume than the DEEP experiment. And there's also a development team that's working on the potential to go to hundreds of tons of liquid argon, which would be situated back at SNOLab, because the collaboration feels that for the final ultimate detector, the depth of SNOLab and the low radioactivity conditions are essential. The experiment called DarkSide, which is situated at the Gran Sasso laboratory in Italy and will start in 2026, start to fill with argon in 2026. Now, that way I'm somewhat involved and having an overview of both of those experiments. Since I retired, I don't supervise students anymore, because particularly since the Nobel Prize, I'm traveling so much that it wouldn't be fair to students to try to take them on as a supervisor. But I still interact with students that are working here at Queen's in the group working on those experiments. And I'm having fun in the process.
Oh, that's good. Fun is the important part.
Indeed.
Well, since we're almost done, I'm going to ask you the question I ask everybody who comes on this show. What do you think has been the most impactful or the most important experience or moment in your physics career? If you can't think of one, it's okay to have 2 or 3 moving about. But yeah, what do you think is the most impactful experience?
There are a number of times that one has those sorts of experiences. It's when you work hard on a project and the final answer finally becomes clear with sufficient accuracy to be believed. And so I guess the most important one is the one for which the Nobel Prize was awarded, but it was also one in which we were able to experience it as a collaboration. because the way in which we worked on the analysis, which was taking place, across the world, U.S., Canada, UK predominantly at that time, around 2001 and 2002, where we blinded ourselves to the final result so that people doing the analysis would not be inclined to adjust the analysis parameters to fit their favorite favorite of the various conclusions one could draw. And so basically on one day, we would have a opportunity for everyone at the same time to know what the answer is when the blindness conditions are removed. One example of blindness conditions is adding in false data that looks very much like, in fact, as much as possible like real data in the experiment, but is with a multiplying constant that nobody is able to know except a couple of people that have been assigned for that. And then that data is removed and you know what the final answer is. And so it really was a eureka moment for everyone when we discovered that what we had been able to do is to prove that neutrinos change from one flavor to another with a part in 10 to the million, with only 1 part in 10 million probability that was not a correct conclusion. So a real eureka moment, and one I remember very clearly.
That sounds like it. Well, now that we're coming to the end of the show, I'd just like to wrap up by saying again, thank you very much, Dr. McDonald, for coming on my little physics podcast. It's really been an honor to have you and truly a pleasure to have you on my show as well.
Pleasure for me too. And I once again, Owen, I applaud you for doing this. And I hope that that this information is of value to students like yourself. Thank
you.
Bye now.
Bye. You've been listening to an episode of The Quantum Mic. Special thank you to Dr. McDonald for coming out on the show. The Quantum Mic was written and produced by Owen Dara, and the interviewer in this episode was Owen Dara. If you're interested in more of our content, you can find our episodes on Spotify or wherever you get your podcasts. Stay tuned for another episode coming soon with another interview or more interesting scientific information. Have a good one.